312, dynamic systems and control. There are two ways to do linear control. One is in the frequency domain, and one is in the time domain. When you took it in 312, you did it in frequency domain, so Nyquist, root locus, and so on. What we're going to do is we're going to do in the time domain. There's a useful idea called state space, which we'll be introducing. So this will sort of complement 312. It is not a substitute for 312, but I think it's very important to learn this way of doing control over using what you learn in frequency domain in that course. So to motivate this, we'll take a simple spring mass damper system. We'll write the equations of the spring mass damper system, and then we will control the system. Okay, so we have two masses connected by a spring, two springs in fact, and we'll assume that we have control over some of the, we have some forces which we can apply. So let's say that we apply a force U2 on this one, and then apply a force, well actually U1, there'll be an equal and opposite force here. And then of course movement is in the x direction. So one-dimensional problem. Okay, so we will, number one, derive the equations, and then use linear control. Okay, and this will be in time domain. So most UG courses do this in frequency domain, and that's what we will not do. So I think it will be new to most of you. Okay, so I think I have enough time to derive the equations. So first step, derive the equations of motion. We'll use the same method as we've done in this course, which is use the Euler-Lagrange equation. So we write the kinetic energy. It's going to be 0.5 m1 q1 dot square plus 0.5 m2 q2 dot square, and then V equals, here the potential energy is not due to gravity, but it's due to spring force. So that is 0.5 k1 q1 square plus 0.5 k2 q2 square. Sorry, my bad. This is not right. So for the spring 1, you can see the stretch is q1, but for the spring 2, since q2 and q1 are both moving, this will actually be the difference between the two. Okay, so the Lagrangian is T minus V .5 m1 q1 dot square Okay, so the first equation, we do d dt of dl dq1, well, should dot minus dl dq1 equals all the external forces, so that will be u1. So when you basically do this, well, let's see what this u1 is. By the way, I think it is, yeah, u1 actually acts, if you see, u1 is acting in the negative x direction. So I need to take care of the sign there. So it will be negative u1. So once you do this, and I will not go through this because we've done this several times, the equations comes out to be like this: m1 q1 double dot plus k1 q1 minus k2 q1 minus q2 equals minus u1. So we can write q1 double dot equals, I'm going to move all the q1, q2, everything on the right side. So what I get is minus K1 divided by M1 plus K2 divided by M1 Q1 plus K2 divided by M1 Q2 equals, oh sorry, no equals, it will be minus U1 M1. So this is my first equation of motion. Very, very straightforward. You could do this using Newton's method. That's what you might have learned in a dynamics course. Next, we can do the same thing for the second degree of freedom. dl dq 2 dot minus dl dq2 equals. Now, when you're writing the external force, if you see this figure, we see that this force is on the right and U1 is on the right. So it's going to be U1 plus U2 for the second force. Okay, so simplifying the terms on the left will get M2 Q2 double dot minus K2 U1 minus Q2 equals U1 plus U2. So I'll solve for Q2 double dot will be equal to K2 Q1 divided by M2 minus K1 Q2, sorry, K2 Q2 M2 plus U1 divided by M2 plus U2 divided by M2. Okay, so that's the question number 2. If we write this in what is known as the state space form, and then we'll call it a day. So those are equations which comes from Newton-Euler. We want to write in the form as several first order equations. That's the state space form. Okay, this is our second order equation, but when we integrate, we always have to write first order equations. So what we'll do is we'll define new variables. Let's call these x1, that will be q1, x2 will be q2, x3 will be q1 dot, x4 will be q2 dot. Okay, so once we've identified these variables, okay, we have to write the equations now only in terms of x's, not in terms of q. So x1 dot, okay, x1 dot is q1 dot, but q1 dot is x3, x2 dot is q2 dot, but q2 dot is x4. That takes care of those two equations. Now x3 dot is q1 double dot, right? So q1 double dot, if you go back right here, this is q1 double dot. So I need to write this equation, the first one, in terms of x1 and x2. So this will be x1, this will be x2, and those constants will stay there as it is. So let me write that down. So we'll get minus k1 plus k2 divided by m1 x1 plus k2 divided by m1 x2 minus u1 divided by m1. And then x4 dot, what is x4? x4 is q2, and so it's q2 double dot. So if you go here, that's q2 double dot. I'll write it in terms of x1, x2 again. So x4 dot equals k2 divided by m2 x1 minus k2 x2 divided by m2 plus u1 plus u2 divided by m2. Okay, one more step and we'll call it a day. We'll write this as a matrix equation because that's how we would like it. x1, x2, x3, x4. So we'll write x1, x2, x3, x4, and we'll fill this a matrix. So it will be this is a 4 cross 1, so there will be a 4 cross 4, and that will be 0, 0, 1, 0, 0, 0, 0, 1. So that takes care of these two equations. Then we have K1 plus K2 divided by M1, K2 divided by M1, 0, 0, K2 divided by M2 minus K2 divided by M2, 0, 0, plus something else times U1, U2. These are controls. So you can see that first two equations have 0, 0 for controls. The second one has minus 1 divided by M1. Oh, well, there are two of them, my bad. This should be a 4 cross 2, right? So 0, 0, 0, 0, and then 0, no, minus 1 divided by M1, 0, 1 divided by M2, 1 divided by M2. So it's all consistent, 2 cross 1. Okay, just let me write one more thing and I'll let you go. Just take this, copy. Okay, so this is x dot. This thing is called A. This thing is called X. This is B. And this is U. So you'll often see this kind of form written down in textbooks or other places. This is the linear equation because there's no squares involved. And this is the state space representation of the system. Now I'm going to call that the uncontrolled case. So in this case, if the control is 0, that is U is 0, then the system reduces to x dot equals AX. And this might be something you've looked in the frequency domain too. To check the stability, I mean, in the frequency domain, you might have taken the Laplace transform of this, and that gives you something like S minus AI, and then you find the eigenvalues of that. You can do the similar thing for this system. So to compute the stability, or to check stability, do the following. First, compute eigenvalues of A. And the way this is done is you take the determinant of A minus lambda I equals to 0 and solve for lambda. These lambdas are unknown. These are the unknown eigenvalues. The second step is now when you do that, if you have an equation like that, it could be, in this case, that equation will be fourth order because you have a fourth order system, right? You have 4 variables, x1, x2, x3, x4. So a fourth order equation could potentially have real eigenvalues or complex eigenvalues. So if you have, no matter what eigenvalues you have, what you need to do is, if you check the real part of all the eigenvalues, if the real part of the eigenvalues are negative, then the system is stable, else not. Okay, so for system with 4 eigenvalues, you check the real part of all the 4 eigenvalues. If any eigenvalue is positive, that means the system is unstable, which means it will basically deviate from, it will basically go unstable, go to infinity. or it won't stay near the zero. So an example is if you take a simple pendulum, a pendulum which hangs down, the eigenvalues of that are actually negative, which means stable. It always goes down to the zero position, which is downward position. If you take the pendulum and invert it, you make it go up. You basically write the equation such that the top position is the nominal position, that is zero position. And if you try to write the state space form x dot equals ax, you'll find that the eigenvalues are actually positive, which means that the system is unstable. In fact, an inverted pendulum cannot be stable. It will actually swing in such a way that it will eventually end up in the stable downward position. So that can be shown for a system like a simple pendulum. Okay, and then there are other systems where you could do the same thing. Now, there's another aspect which I think is more important for us because we are dealing with a system which has control U. Okay, just because a system is unstable doesn't mean that we cannot control it. Like, for example, the inverted pendulum, we can keep it upright if you have the right control. So controllability asks a different question. It says if the system has some control, like U, the question is, can we control it? And there's a definition for this, which I'll write down for controllability. So the definition is a linear system is controllable if and only if it can be transferred from any initial condition or let's say any initial state x equals x0 to any terminal state. X equals xt in finite time. Okay, so it's kind of interesting. So if you have a pendulum at 0, 0, where 0 is the angle and 0 is the velocity, there's two things which determine the pendulum. It's saying that you could go to any other position, so 0.5, say, position, and minus 0.5 of velocity in finite time, then the system is controllable. Okay, very broad definition. The question is, how do we even use this definition to figure out if a system is controllable or not? It turns out there's a very simple way of doing that. It's called a controllability matrix, and I'm going to define it now. And I'm not going to do the derivation, but what we do is we set up a controllability matrix which is like this. It's called that CO. Okay, it's defined as follows. Since we know that the system has a matrix A and B associated with it, and we know n, which is the degrees of freedom of the system. So for an example I showed you, n equals 4 because there are 4 states. So an minus 1 times b, an minus 2 b, comma, so on, till then we have a square b, ab, b. Okay, so compute this matrix called the controllability matrix. Here n is the dimension of x. So if you have x dot equals ax plus bu, we have for a, we have n cross n. You typically assume that there are m controls. So this b would be n cross m. Let me just write it differently. So x dot equals ax. So n cross n, n cross 1 plus b u. This will be n cross m, m cross 1, n cross 1. So you can see the matrix multiplication makes sense. And then the b is the number of controls. This is controls, and then this is the number of states. And the same thing is here. So you need n in order to compute CO. Now, once you control CO, to check controllability, this is what you do. If the rank, okay, this is something which I'll not get into, but a rank is basically the number of independent rows or columns in the matrix. So if the rank of CO equals n, then the system is controllable. And if rank CO is less than n, system is uncontrollable. Okay, so it's as simple as computing CO, controllability matrix, and then essentially figuring out what the rank is. So to do this, you could set up this controllability matrix and then check for rank, but Python makes it easy for you. You can install a package called control, and then you can actually compute the controllability matrix by importing control, the package control, using this command ctrb. Ctrb is controllability. You supply it with A and then B, and then to find the rank, you just need the linear algebra package and just say matrix rank of CO. And if that rank which you get is n, then it's controllable. If not, it's not controllable. Okay, so I think I have an example which shows exactly how to do this. Let's see that example. Yeah, very short code. Okay, so here's what I did. I took the spring mass damper system, which I wrote down earlier. Okay, okay, so I'm importing NumPy and control. The parameters, I just put some mass and spring constant. I compute A. This is just setting up the A matrix from the nodes, setting up the B matrix again in the nodes. Here I compute the eigenvalues of A. So I said, how do you check if the system is controllable or not? You check the eigenvalues, so that it'll do that. Then I find the controllability matrix, which is saying using CTRB. And then I find the rank of the matrix. Okay, so there's like some extra stuff which we can ignore for now. Yeah, I need to comment this out for now. So I think this is a way to comment out multiple lines. Okay, so let's run this. Okay, so what we get here is, it's a bit hard to see, but here it is, eigenvalues uncontrolled. This is I'm trying to figure out if the system is stable or not stable, the spring mass damper. You can see the eigenvalues are, that is actually almost zero. It's 1e negative 17. So there's a complex eigenvalue. So you see a j component there. Then there is minus, again, 0 minus something times j. And then there is, again, almost close to 0, something times j, and then close to 0. So what you observe in this case is that the eigenvalues are actually, the real part of the eigenvalues is actually 0. And then the complex part of the eigenvalues, with this thing in front of j, is positive. Now, when the eigenvalues are on the imaginary axis, so to say, the system is actually called neutrally stable, which means that It's not unstable, not stable, but it will be neutral stable. What it means is for the spring mass damper is because there's no damping, there's no damper sucking out energy, it'll just keep shooting back and forth forever, right? Won't stop, just like a pendulum. So that's what this eigenvalues are telling you. Uh, Again, if you look at the rank of the controllability matrix, it says 4, and the state space is 4, which means that the system is controllable. That is, you can get the system from any point x equals x0 to any other point x equals x of t in finite time. Okay, so we'll go to the control part next. So once we have determined the system is controllable, we can do the next part, which is trying to uh, uh, do the control part. So here are two methods to do control, and we'll do both of them, and I'll show it on the same example. Okay, so number one is pole placement. Okay, this is something you probably did it with root locus in 312, which is you want to put the eigenvalues of the closed loop system, as they'll say, at a specific location. Remember that if you put it on the negative half, if the real part is negative, the system is stable. So your goal is to put the eigenvalues of the system a plus x dot equals a plus bq bu to have a negative real part. So what we do here is assume u equals minus kx, and we know that x dot equals ax plus bu. We sub that in, ax minus bkx, a minus bk times x. Okay, so this is basically going to be, let's call that a tilde x, or a bar x. So now we have a system which looks very much like an uncontrolled system, right? Except that it's actually controlled because k is something which you choose. You can do whatever you want with u. So this k is user chosen. So it's actually a bar is something which you can set to whatever you want by tuning up k, because k is in your hands. So if we want to figure out, if we want to make the system stable, what we do is compute k such that the eigenvalues of a bar, which is a minus bk, have negative real part. Okay, so that's how you would control system. Very simple idea. And this is what root locus actually does for you. But it'll do that in the frequency domain, I think, right? Yeah, frequency domain. So how to do this in Python? Well, it's very simple. You just do this. You say control dot place. Place is a function within the package control. You specify a, b, which are system parameters, and then you specify the poles. This is the user chosen poles or locations of eigenvalues. This is something which user chooses. So you want to put it at minus 100, just do it. Just put p equals minus 100, minus 100, minus 100, 4 times. That'll do. So what it does, it actually gives you k. So this is the output, right? And that k, when you implement it, it'll give you what you want. It'll place. So that's the equivalent of root locus. Okay, the second thing I'm going to show you is actually more powerful than what you've ever run in 312. It's called a linear quadratic regulator. So the second idea is linear quadratic regulator, LQR. This is something which is very, very famous. It's very well adopted, and you might hear people saying that I used an LQR, and this is what they're doing. What they're doing is they're solving for an optimization problem. J is the cost. We've talked about optimization a little bit before. This optimization is X transpose QX. I'll define what those are. U transpose RU plus 2X transpose NU dx. This is the cost. Q R N are user chosen matrices. That is, you will choose them to whatever you want. Again, I'll tell you a little bit about choosing them a little later. X is the state. U is the control. Okay, we'll assume that the state is n cross 1. The control is m cross 1 like before. So you can see that Q would be n cross n, right? When you put n cross n, you'll see that X transpose QX comes out to be n cross, sorry, X is n cross 1, n cross 1, so X transpose is 1 cross n, Q is n cross n, X is n cross 1, and so this whole thing, multiplication, will give you 1 cross 1. So it's a scalar. A cost cannot be a vector, it has to be a scalar. Similarly, if we'll put R will be m cross m, and so you'll see that when you do U transpose RU, you'll have U is m cross 1, so 1 cross m, m cross m, and then U is m cross 1. So when you take this product, you'll have 1 cross 1, which is a scalar. So everything has to be a scalar. And then finally, n would be n cross m. So X transpose NU would be 1 cross n, n cross m, m cross 1. So the whole thing is 1 cross 1, which is also a scalar. Yeah.
What's an example?
This one, almost everything can be controlled by this. So simple pendulum, you can do it. Cart pendulum, you can do it. Double pendulum, you can do that. Control a differential drive car, you can use it. It's very, very, very broad. And we'll get to an example soon. Okay, so I've shown you a cost. And as you know, this is this particular problem, which is minimize this, is an unconstrained optimization, right? We've talked about unconstrained optimization. So when we do unconstrained optimizations with a computer, we can use what's that? Fmin, well, fsolve. Oh, no, not fsolve. What is the one which is in, I forget the function in Python, but there's a function which we've used for these optimizations, right? Now, using that function will make it very time consuming. And the reason why it's so popular is because for that particular equation, the cost, it turns out there's an analytical solution. And that is why it is very, very popular. So the analytical solution to this, and we'll not get into the details of how this is computed, there is an analytical solution to the unconstrained optimization problem. And the solution is, first of all, u equals minus kx. So that's the same solution as what we did for pole placement. It can be shown that it is of this form. It's a feedback form. This is a feedback form, right? It's like a PD controller, but it's really more than that. X is a state, so it could have position, velocities in X, so K is position gain, velocity gain. The solution is actually this. K, which is the unknown, is minus R inverse P transpose P plus N transpose. Okay, so in this equation, R is known, is something which you specify, if you go back, you specify R, you specify Q, you specify N. X dot equals AX plus BU is given. I should write it down here. X dot equals AX plus BU. That's the system which we know. So this is known, B is known, N is known. So this is an unknown. What is P? Turns out that P is the solution to this particular equation. A transpose P plus PA minus PB plus N R inverse P transpose P plus N transpose plus Q equals 0. Okay, so this equation is very famous. It's known as the Riccati equation. Okay, so what we do is, step 1, solve for P using Riccati equation. The second step is compute K from, let's call this star, from this. There's 2 steps. So the first step, the Riccati equation, this looks like a non-linear equation. Right? It's actually non-linear. There's P, this linear, but then there's this part which has P and P, so it's like a squared. But there are ways to solve this very quickly. So you really don't have to, I wrote it all down just for information. You really don't need to ever compute the solution to this. All you do is to KPE equals control dot LQR A B Q R N. So you supply it with the system dynamics A and B, and then you supply it with the user chosen values for Q, R, and N, and lo and behold, you will get KPE. K is the feedback gain, P is the poles, U equals minus KX. Remember that. This is the poles, right? Here we couldn't control the poles location directly, but indirectly by controlling Q, R, and N, you can control the poles. And E is actually the eigenvalues of A minus BK. So it does that for you. You don't have to do it separately. Okay, so it all boils down to doing one single thing, which is you need to compute QR and N. So the most challenging part in LQR is, well, first is to write the equations in linear form. In this case, we don't have to worry, it's linear. There'll be another step involved if it's nonlinear. We'll get to that later. But the challenge is how do you compute Q, R, and N? So this is where usually people struggle, and that's where I would give you some recommendations. Okay, and this is your 4th project. Will actually require you to sub in Q, R, and N. That will be your project. And you'll see it's sometimes not very straightforward. So how to choose Q, R, and N? So what I do is I usually take n equals 0. That's it. Makes life easy. So don't have bother with n. It's basically a cross-coupling term between, let me write the cost. It's x transpose qx plus u transpose ru plus 2x transpose nu dt 0 to infinity. Okay, so to make your life easy, this is what I suggest. Just take n equals 0. Don't even bother with n. Just make it 0. So it'll be, so that term will drop out. Okay, now what is q and r doing is kind of interesting. When you have this term, so look at x transpose qx. For a second, just think x is a number, like one state. X and q is going to be one state. It's going to be one value, a scalar. Okay. Now, if you put a very high value on q, say 1,000, then even small changes in x will make a very big value for x transpose qx. So the bigger the q is, the more penalty is given for deviation in the state. Big q, more penalty on state deviation. So here you're trying to go to x equals 0 because you have x. If you're not going to x equals 0 and you're going somewhere else, you just put x minus whatever x ref. Similarly, if you look at u transpose ru, you can say the same thing. Big R, more penalty on control. What it means is that if you put a very big value of R, it will penalize you for putting control. So even a small torque will lead to a high cost. Okay, and so it's really basically a compromise. You need to figure out how much deviation can you tolerate. There's how much x can you tolerate and how much u can you put in. And so you need to basically choose a number which basically gives you a compromise between the two. So this is just a one scalar example, but how do you do it for something which has 4 states? So what you will do is this, q, set it up like this. So it's a n by n matrix. So put q1. So let's say the first state is x1. So take the max of the state. Let's put it max x1 square, q2 max x2 square, and so on. So you make a diagonal matrix like this. So remember that when you have a state, position, velocity, and so on, they have different units. And so by normalizing it, this is normalizing, you're basically making it dimensionless, so to say. And so now you can choose q1, q2 effectively. So then these are free parameters, this one, this one, this one. So then you slowly ramp them up from 0 to whatever value you want. Not 0, you cannot take 0. You need to have a q, I think, can be 0, but r cannot be 0. Okay, so what you can do is you can tune it up to some value, but now those numbers are, so instead of having an n cross n matrix, which has n square entries, you're just making many of them zeros and just tuning up just n numbers. Tune only n numbers, which is, I think, is easy. You can set up like you can sweep through you can have a if for loop and sweep through them and see what the performance is of over n numbers. You can do the same thing for r. So choose r like this. 1 divided by, sorry, r1 max u1 square, r2 max u2 square, 0, 0, and just keep doing that. Okay, so again, it achieves the same thing. Now, here I'm assuming that your controls are different. Maybe if one of them has torque, one of them you're controlling, U1 is torque, U2 is some kind of position or voltage. In that case, you will not non-dimensionalize like this. But if you have all of them are torques, all of them you have Newton meters, then what you can do is actually you can do something more simpler than this. You can actually just get rid of this whole thing. Right? If all U's are torque, then just do it this way. R1, R2, R3, so on till Rn. Because the non-dimensionalizing doesn't really help you here. Just use that. And then tune Rn numbers. Okay, so when you do the bicopter, actually, you'll see how to do this. This is like a very good exercise, I think. Many systems are controlled this way. I'm going to show you the same example, the spring mass system using this technique, both techniques, in fact, pole placement and this, and the one I talked about. So here I commented out this code. Let me uncomment it. Okay. Okay, so nothing interesting is going to happen because there's no animation associated with it. So it's just going to show the output of using those two commands. So pole placement, I chose my poles to be at -1, -2, -3, -4. All of them are negative. Real part is negative, so it's stable. I use K, control, place, and then again the eigenvalue, eigenvectors. So for part 2 LQR, I set my R to be, so you can see I did the second thing, which is, in this case, both the controls are 4. The controls are 4, so I just have one single thing, 0.001. So R1 equals R2 equals 0.001. This is just saying that the smaller the R, the more I'm letting U to be deviate from 0. So a lot of control effort. And then Q, I just chose to be I. Okay, now this is just simplest thing to do is just to choose I. So what I have here is actually a very simple way of controlling it. You could try this, and then if it does not work, then you want to do something more fancy, like the one I told you. Here is control LQR and then eigenvalues, same thing. So let's run this. And we'll focus on the second part, which is the new part, because this code, oh, it's done. So first part, pole placement. This is the feedback gain. You can make no sense of it, right? Why is it even choosing -0.1? It's very hard to figure that out, but it actually does its job of putting poles at -1, -4. That was the closed loop gain. LQR, you do the same thing, which is different way using Q and R. It also gives you the eigenvalue uncontrolled system of the control system. You can see the eigenvalue is actually -15. That's very, very good because it's more and more further away from on the real part of the x-axis. So it's the more negative it is, the faster it will go to 0. -5, -1, -1. Now maybe you're not happy with this. It's -1. Maybe it should have been a bit more to the left. In that case, the only way you can do this with LQR is to tune this Q and R. That's the control here. You cannot directly place the zeros, but the other one, pole placement, will put the zeros where you want. Okay,